Hi, I'm Azra Hafiz and I'm your TiNKA educator. So welcome to TiNKA Lightboard series, and before we begin, don't forget to follow our social media, click like and follow our Facebook and Instagram on the link below. Alright, so for today, we're gonna learn about free falling, a continuation of chapter 2. Alright, so in chapter 2, we already learned about how object move in a straight line, but now we're gonna talk mainly on free falling. So what is free falling? Free falling is object that falls following gravity. So just imagine two different objects of same mass, right? So if I were to drop it from the same height, they're going to fall at the same rate. However, assuming one of these objects have a different shape, they have a bigger surface area. Now, an object having a bigger surface area will cause it to experience a resistance. And this resistance is due to the air particles surrounding us, creating an updraft. So what happened is that when the updraft is created, all the objects that is falling will rely on this resistance to fall on its speed, whether it's going fast or going slow. But free falling, as it obeys the gravity, the acceleration is always constant. Which is, we learn that the acceleration of our Earth on the equator is 9.81 meter per second square. And this gravitational acceleration differ from places and differ from different height. When we look at our North Pole, the gravitational acceleration here is found out to be at 9.83. And when we go to the outer space, for example, the moon, the gravity of the moon is 1/6 of the Earth. And then when we look at Mars, the gravity is much smaller than the gravity of the Earth. We're going to talk about the gravitational acceleration and how the gravity affect objects when we go to chapter 3. Now let's look back at our free falling. Now, if an object falls from a high position, let's say you were to drop a ball. This ball will have an initial velocity of 0. We put the symbol as U, and this is 0. As the object moves downward, gravity is acted upon it. What happened is, this gravity is a force, and this force is pulling down. So, as the object moves from first position to final position, the V here will eventually reach the maximum value, which we put this as the final velocity. And you must remember, your gravity is constant at 9.81. We learned in the earlier chapter 2 where we can use the formula to determine the speed by using V equals to U plus 2as. Put your square here. So from here, we can find the height of the building. Let's say I'm putting here as 20 meter. We can determine the speed of the object, the final speed of the object by putting in our formula. So when you calculate, eventually you get your final answer. Alright. Alright, to show you how the free falling goes, here I have two similar papers. Now, both of these papers have the same mass, but on one paper, I'm going to crumple it up. what happened here, I'm decreasing the surface area of the object. On this side, I'm leaving the paper as it is. Both of them have the same mass. Regardless whether I'm crumpling it up or I'm leaving it as it is, the mass does not change. Now, if I were to drop both of these objects downwards, you can notice that this crumpled paper will move faster compared to this open paper. Why? It's because for the open paper, the gravity is acted upon it, but there is also resistance, which is the air friction. As opposed to the crumpled paper, this crumpled paper, they still experience the air friction. However, the amount of area that is exposed to the air friction is smaller compared to the open paper or uncrumpled paper. So eventually here, the resultant force is much smaller than the resultant force here. So due to the difference in the resultant force, this one will move with a smaller velocity and this one will move with a larger velocity. Alright? Stop. To continue our topics, today we're gonna continue on the topic of inertia. So what is inertia? Inertia is also known as the Newton's first law. Now, what does Newton's first law state? Newton's first law states that an object at rest. For example, let's say we have a block of wood here and it is resting on top of a table or moving with a constant velocity. For example, the car that we have here will remain in its state until an external force is applied on it. Now, what does this mean is that this block of wood will be acted upon gravity. And opposite of the gravity, we have our normal force. To the left and to the right, we have the same force acting on the object. Nothing is moving it. So it will remain in this resting state, unmoving, until you apply an extra force. Let's say you push the block of wood, then only this block of wood will start to move. If you do not apply the extra force, this block of wood will just remain in its original state. Alright? The same thing that is happening to this car. It is moving with a constant velocity, not accelerating, not slowing down. So here, what we have is a car that is moving, relying on the thrust of the engine, which is equal to the frictional force. That is acted on the car. So here, your thrust is the same value as your frictional force. On this state, we call this as forces in equilibrium. It won't change the state of how it moves. Let's say suddenly you try to slow down your car. You let go of your oil pedal or you apply force to your brake pedal. So what happened here is that you're going to increase the frictional force. and you're going to have the car slowing down. Why? Because here it experiences changes in force. So remember, when we talk about inertia, we talk about an object will remain in its state until external force is applied. And we know that inertia is only affected by mass. What does this mean? Is that an object having larger mass would experience larger inertia. Alright, so when we look at two different animals, for example, we have the elephants and we're going to take the house cat. Now, you've seen both of these animals through television or at the zoo. What you can notice is that when a cat is running, it can move in a very zigzaggy pattern and they can shift their direction very fast. As opposed to the elephant, because of their larger mass, what happened? When the elephant moves forward, it is harder for the elephant to slow down. It is harder as well for the elephant to change its direction. We can see this not only in animals, we can also see it in vehicles. Smaller cars can maneuver easily compared to larger trucks. And now we're going to take a look at some of the questions that can come out for your examination. Now, on one side, we have the harbour. We have two different kind of ship. The first one is the one that can carry huge number of containers, where we call it this as carrier or tanker. And the other one, let's just say this is a fisherman's boat. Now, what happened here is that the mass of the tanker has a bigger value compared to the fisherman's boat. Looking back to what we explained about inertia earlier, we know that objects that have a bigger mass experience a larger inertia. It is harder for them to move, it is harder for them to change direction, it is harder for them to stop compared to object that has a smaller mass. So for this tanker and fisherman's boat, what happened is that if the fisherman's boat need to stop, they can cut off the engine somewhere here. Why? Because of the smaller mass, the effect of inertia on the boat is much smaller. They require lesser force to stop. However, for the tanker, they need to start to cut off their engine somewhere here. Why? As they cut off the engine, this tanker will keep on moving due to the effect of inertia. It will keep on moving until it almost reaches the harbour, where eventually the captain will start to turn on the engine on a reverse. Why? Because they don't want to hit the harbour. There are some tankers that are able to stop way before the harbour, but the problem with that is that you tend to overestimate your distance or underestimate how far you are from the location that you need to stop. When we look on the other side, we have two kids. One have a small mass, the other have a bigger mass. Here what happened is, in the smaller mass, it is easier to start the swing. Because this kid has a much smaller mass, the effect of inertia on the kid is much smaller, easier for him to start moving. On the other side, his friend having a much larger mass will experience some trouble to start to swing himself, but as we look further, what happened here? This is the first to stop. On the other hand, his friend will continue to swing because the effect of inertia will allow the boy to keep on having a bigger oscillation than his friend. Now, we look into safety and precaution when we are talking about inertia. When you're inside a car, let's say your parents start to move from a rest. The car is stopping and then it started to move. What you're going to experience with your body is that you're going to lurch backward. Why? Because your body inside the car is only experiencing gravity. So as the car moves forward, you will start to lurch backward. The same thing happen when if let's say suddenly your parents start to stop the car. Because your body is still experiencing the forward motion, what happens is, when the car is stopped, you will start to lurch forward. Due to the effect of inertia, you will experience this. Now, how is this related to safety and precaution? We can see inside cars, they have seat belts. How is this a safety and precaution? Is this seat belt will hold the driver and passenger in place during accident. Now, let's just say you're inside a vehicle and you are met with an accident. Your car is hitting something. Now, because of the car having a bigger mass, it also creates a larger force. So, if let's say seatbelt is not around, when the car suddenly stops, the body will keep on moving forward, and there are cases where people who do not use the seatbelt are thrown out from their vehicles. So that's why the seatbelt uses the concept of inertia to hold you in place. Aside from seatbelts for car, we have the airbag. The airbags, they use the concept of inertia as well as impulsive force, where it reduces impact of the head to the steering wheel. And done. Now we're going to take a look at inertia on other objects. For the safety precaution, for example, we have a tanker carrying liquid. It can be flammable liquid, it can be highly explosive substance. Now, how do they carry this liquid without harming the driver as well as the car surrounding it? They separate the liquid into 3 different compartments. Each compartment will have a different mass of liquid. On the end of the truck will have the